Greetings, we are from Group 7 and we are going to do a demonstration and explanation about the heartbeat sensor using Arduino.
Module 1.1, read the analog input, potentiometer, and serial monitor. First, prepare all the components. We need ESP32, micro USB cable, potentiometer, breadboard, and jumpers. This is the connection diagram. Connect the component based on the diagram. Connect USB cable to a laptop. Connect micro cable to ESP32. Copy the coding from module 1.1 and then upload to Arduino IDE. Compile the coding. Upload the coding to ESP32. Press the boot button for 3 to 5 seconds while connecting status. Look at the output from serial monitor. Because we get 0 for our threshold value, we need to rotate the potentiometer to get our threshold value. So the threshold value changes as the potentiometer rotates. And lastly, for module 1.1 is coding explanation. First line is to start analog reading from pin 4. Third line initialize serial communication. Fourth line process the program for 2 seconds. Line 7 reads the value from the analog pin A4. Line 8 send the value stored in the threshold to the serial monitor. And last line is pauses the program for 10 milliseconds before taking the next reading.
Module 1.2, read the analog input, potentiometer, and LCD display. We need to maintain the connection from previous module. Add LCD to the breadboard. This is the connection diagram. Connect the LCD to the breadboard. Then we connect USB to the laptop and connect micro cable to ESP32. Next, we copy coding from module 1.2 and update the coding in Arduino IDE. Then compile the coding and upload the coding to ESP32. At the same time, we press the boot button about 5 seconds while connecting the status. Wait until LCD show display and lastly, we rotate the potentiometer to change the threshold value. For coding module 1.2 explanation, first row is input LCD library, row 3 is LCD parameters, row 6 is for turn on LCD backlight, row 10 for print threshold on LCD equals 00, row 14 is print threshold value equals 11, and row 17 is delay for 1 second.
For module 1.3, read the analog input and microphone module. We can maintain the connection and add this microphone module following this connection diagram. Connect USB cable to laptop and connect microphone cable to ESP32. Copy the coding from module 1.3 and update the coding into Arduino. We compile the coding and upload coding into ESP32. Press the boot button while connecting status and we will wait for the output. The output will display time elapsed, threshold value and also raw value. Press the Arduino and launch Beta Serial Plotter and then choose the correct port and baud rate. Click plot all data and zoom out until you see all the data signal. Adjust the threshold value until it is above raw value. Observe the threshold value on the LCD, and this is the data output signal for normal sine. Knock the mic to give some analog input and the graph started to receive input from the microphone. For coding explanation, on line number 3, we need to include float as data type in number and set t equals to 0. For line 16, it represents the time elapsed in milliseconds. For line 20, it will wait 10 milliseconds before continuing. Line 23, it will display the time elapsed. Line number 25, it will display the raw value. Number 27, it will display the threshold value.
Maintain the connection from previous module. Copy the coding from module 1.4. Compile the coding and upload the coding into ESP32. Press the boot button for 3 to 5 seconds. Close the Arduino IDE and launch the Beta Serial Plotter. This time the new data has been added. Adjust the threshold value until the value is above the raw value. Then click the Add New Plot to add the third data on the new plot and disable the third data on the first plot. Knock the mic to give analog input to signal. So every time the raw value exceeded the threshold, it will detect as input. So the new coding function is the signal peak data is detected whenever raw value higher than threshold, and it will show the result.
In this module, calculate BPM using input from a microphone, and then we are going to display the calculated BPM on an LCD, and we are going to compare the results with the mobile app. So first we will maintain the connection from the previous module. We need to copy the code from module 1.5 into our Arduino, and we need to compile the code to check for errors. Upload the code to your ESP32. While the ESP32 is in the connecting status, press and hold the boot button for 3 to 5 seconds. And once the ESP32 is ready, connect the status code tube to the microphone, and that's our input source. Now we'll test the setup using two methods. So method 1, we need to place the stethoscope on our chest and let it detect our heartbeat directly. And for method 2, we need to place 2 fingers on our neck to feel our pulse. And we tap the microphone every time we feel the pulse, and the signal detection system will pick up the input. So the BPM calculation process will start, and it will take around 15 seconds for the BPM to calculate accurately. The threshold detected is 1453 and the BPM is 79. And through the app, the BPM calculated will be 81. Let's dive into the code and break it down. Line 5, this line holds the last timestamp when the BPM was calculated. Line 7, it counts the consecutive deductions of a valid signal. Line 8 keeps track of the number of beats detected in the current interval. Line 9 calculates the beats per minute, which is BPM. And line 17 displays static tags such as threshold and BPM. If the signal is valid, it increments the count, as in line 26. For line 31, if the signal isn't valid, it resets the filter wave to 0. For line 34, if the signal is detected more than twice, it confirms the heartbeat. Line 37, it calculates BPM by multiplying the detected beats by 4, scaling it to a 15-second interval. And line 44, finally, if the calculated BPM is within the range of 60 to 120, it displays the value on the LCD.
So this will be the final result for this project.
This is the reflections and lesson that we got during doing this project. For reflection, you can use the MS4416 microphone module as a replacement for hard pulse detection in BPM simulation. Additionally, it is possible to incorporate the result of the signal from module 1.5 into the process. These are the lesson outcomes that we got during doing this project. First, understanding how to calibrate sensors and threshold for accurate reading is critical, especially when working with sensitive hardware like microphones. Second, learning how to implement noise filtering techniques, for example, using software filters or hardware shielding to improve signal accuracy in noisy environments. Third, enhance troubleshooting skills when identifying and fixing hardware or software issues, such as bot errors or driver incompatibility. And lastly, learning to process raw analog signals into digital data for meaningful interpretation, such as converting signal peaks into BPM values.
Challenge and solution. The challenge we faced while carrying out this project were unclear display on LCD, an overly sensitive microphone, port configuration errors, and difficulties in BPM calculation. So, we successfully resolved this issue by replacing the provided LCD with 20 times 4 LCD. For the microphone, we conducted the simulation in a quiet environment. To address the port configuration error, we installed the correct driver for the PC and selected only functional ports. Lastly, for the difficulty in BPM calculation, we adjusted the threshold to achieve an accurate heartbeat measurement.
And that's it. Thank you very much.